Alright, this is a video I've been wanting to make here. I should have made this earlier, but it'll be good practice for your test that'll be coming up here. So it's the Unit 1 Constant Velocity Practice Sheet, and it's just really trying to get you geared up on all the different things you could see involving constant velocity motion. So this first one is just finding the unknown variable. The formula we're using in all these is V equals d over t. Alright, so it's just a matter of you're given two of the variables, solve for the third. So we have 10 meters per second equals 60 meters divided by t. So we multiply both sides by t. Alright, so we have 10 meters per second, t times 10 meters per second equals 60 meters. Divide both sides by 10 meters per second. Alright, so you get 60 divided by 10 is 6. Meters divided by meters per second. Well, the meters cancel. And what you have is 1 over seconds, which becomes just seconds. So 6 seconds. I should probably write it 6.0 seconds to make it a little bit easier to see. Alright, on to the next one here. V equals d over t is our formula. We know 25 meters per second equals distance over time, which is 30 seconds. So we're solving for distance, multiply both sides by 30 seconds. Sometimes we use parentheses, sometimes we just use that. Alright, so d 30 times 25 is about, what is it, 750? So d equals 30 times 25, which is the seconds cancel, 750 meters. Just gotta pause this for 1 second. Alright, so on to the next one here. We have V equals d over t. So this one we're solving directly, 760 meters in 37 seconds. So 760 divided by 30 is 25 meters per second. I'm only doing 2 sig figs. 25, get rid of that. I only have 2 sig figs on the bottom, 37, so that's good. Then the last one, V equals d over t, but wait a minute, it gave us a delta x. Well, for these problems, delta x is displacement, right? Displacement in lowercase d, distance, they're kind of the same thing for our purposes. It's okay. Equals 1,700 meters in, what am I doing? 157 meters per second equals 1,700 meters divided by t, multiply both sides by t, multiply both sides by 157. Now notice I didn't put the units there. You gotta be careful doing that sometimes. You know, this is meters per second, this is meters per second. I know the answer has to come out to be seconds, 1,700 divided by 157, which is 11 seconds. I know the answer has to come out to be in seconds. So if I've written all the variables down with units once, I don't need to put them all throughout the equation. But sometimes it helps to put the units there just to make sure you're solving for the right things, right? One of the most common mistakes I see are kids not properly identifying variables. Like it literally says V equals 157, so we got to put that in for V. Delta x equals 7, you got to put it in for delta x. However, when it's a word problem like down here, kids will often mix up velocity and distance, time and velocity, and so on. So the key to a word problem is identifying the variables. So right away I'm writing V, D, and T down right here because I know those are the variables that I'm dealing with, that I'm looking for. So how long does it take a car? How long does it take a car? So that's going to be time. How long does it take a car traveling at 55 meters per second? So that's the speed, right? To travel a distance of 1.5 kilometers. Kilometers. I know that better convert that to meters. So 1,500 meters. Okay, so I know the velocity is 55 meters per second. I know the distance is 1,500 meters. I have to make the length, the lengths the same. So the distance unit's the same. So if I'm doing 55 meters per second, I need the distance to be 1,500 meters. If I did kilometers, I would have to make this kilometers per second. So I'd have to like divide this by 1,000. That's just silly. So it's, if you're given distance kilometers, if it's a problem where you're not just solving for speed, then you're going to have to convert it to meters. So time is what we're looking for. So V equals D over T. All right, so 55 meters per second equals 1,500 meters divided by time, so multiply both sides by T. Cancel out there. Divide both sides by 55. Alright, and that's going to cancel out there. We get T equals 1,500 over 55. Alright, that ends up being 27, and then the units on time here would be seconds, because that's the unit time that's used in the problem. How far does a soccer player run? So how far? That's going to be distance we're looking for. How far? That's distance. That's our unknown. How far does a soccer player run in 5 seconds if her average velocity is 4.5 meters per second? So it's going to be 5.0 seconds. V is 4.5 meters per second. So velocity equals D over T. Okay, D over T here, we've got, we can plug in now. So, sometimes I like just solving in terms of the variables and then plugging in. That's kind of a helpful thing. So here's an example of doing that. Multiply both sides by T. So you get D equals VT. Velocity times time. And then you say D equals 4.5 meters per second times T, which is 5.0 seconds. So 4.5 times, is 23, or 22 and a half. All right. How fast is a plane flying? It covers 2,000 miles in 3.5 hours. So how fast is V? So that's our unknown. D is 2,000 miles. T is 3.5 hours. All right, V equals D over T. So it's 2,000 miles per 3.5 hours. I don't need to convert to seconds or meters or anything like that, because my units are hours, my distance is miles, my units on time are hours. We can just solve for it in terms of miles per hour. So 2,000 divided by 3.5. Who knows how to convert it? No one knows that. I mean, of course people actually do, but I'm not expecting you to. All right, on to the back here. So this one, consider the following position versus time graph. Determine the average velocity of the object. So average velocity is the slope, which is rise over run, delta x over t. So rise over run starting at 10, we're going up to 60 in 6 seconds. So the rise here is actually plus 50 meters. The run is 6 seconds. So we've got plus 50 meters in a time of 6 seconds. So 50 divided by 6 is 8.3 meters per second. Mathematical expression describe the motion. Well, you start with y equals mx plus b. The y variable is position, which is a slightly different looking x. M is the slope of the line, which is positive 8.3 meters per second. The x variable is time, that's t, plus the y-intercept, which is 10 meters. Shown below is velocity versus time graph for an object. Describe the motion of the object. Okay, so we are moving forward, positive direction. Forward is the positive direction. And then we quick turn around, we quick move backwards. It's a big change, right? It's going from 4 down to -3, so that's a very big change in velocity. Quick move backwards, and then stop. Something like that. You can describe, going faster forward, slower backwards, because it's 4 meters per second for 2 seconds. Then it instantly changes to -3 meters per second for 1 second. Then it stops. So, draw a corresponding position versus time graph, number the axis. Okay. How far did the object travel from 1 to 2 seconds? Alright, position versus time. So, it's going 4 meters per second each second. Right? So, it's going, let's say, 1, 2, 3, 4, 5 for time. Let's see, we're going to go forward a total of 8 meters. We're going to go backwards 3. So I need 1, 2, 3, 4, 5, 6, 7. Oh, 1, 2, 5, 6, 7, 8. We're using the whole scale here. So if it's going 4 meters each second, in the first second, it goes 4 meters. So it starts at 0. So after 1 second, it would have to be at 4 meters. At 2 seconds, it would have to be at 8 meters. So the line looks something like this. Then, in the next second, it turns out to be negative 3 meters per second in that second. So it's going to go backwards 3 meters. And then, for seconds 3 and 4, the object is stopped. Okay, that's. Oh, I'm making a video. Yeah. No, you're good. It makes for an entertaining playback. So, how far did the object travel from 1 to 2 seconds? So that's from here to here, 1 to 2 seconds. You could get it by the area under the curve, or you can just read it off the graph. You run out of paper, maybe? That darn thing. 1 to 2 seconds. That's from here to here. 4 meters. Just read it off the graph. You can do it either way. Either area under V versus T, or read from X versus T. Find the displacement from 0 to 5 seconds. So 0 to 5, you'd have to find this area, positive 8, this area, negative 3, and add them together, or just read it off the graph. So it's positive 5 meters. Average velocity from 0 to 5. Well, average velocity is actually displacement over time. So it's plus 5 meters overall in 5 seconds, so it's plus 1 meter per second. All right, oops, I don't know if that was on the screen. I'll get this posted as well.